Hi, welcome to Algebra 2. This is Mrs. Brunk. Today we're going to be doing some review on solving equations. And we're going to review the basic steps for solving equations. We're also going to review special cases, proportional and literal equations. And we're actually going to be rewriting formulas and equations for specific variables. So let's go ahead and get started. So there are four basic steps to solve really any equation. And that first step is always if there's any distributing to do. So if you see some parentheses with a number out in front being multiplied, we take care of any distributing as our first step. So distribution would be step one. Step two is to simplify each side by combining any like terms. So second step, add like terms together on the separate side. So clear up the left-hand side, clear up the right-hand side. Step three would be to move variables to one side. So typically what I do is I'll move the variable from whichever side has the smaller coefficient in front of it and move it to the other side. And so again, that's step three would be to move variables. And in order to do that, we would then have to isolate the constant terms on the other side. So our goal is to try to get the variables on one side, all the real numbers on the other, and then if we have a coefficient in front of the variable, we need to make sure that that gets undone by, if it's multiplying by the variable, then we would divide both sides, or if the variable is being divided by a number, then we multiply by both sides on that by that number to undo whatever's being done. So that last step would be then to solve using inverse operations, and that's what I meant by undoing. So if you have some addition or subtraction to do, then you would undo by doing the opposite operation of that, and any multiplying or division by doing the inverse or opposite operation to that. Let's go ahead and look at the first equation to solve. So 6 times n plus 5 equals 2. let's go ahead and take a look at question number 4 as our next example, and we'll leave the other 3 as you tries. So step 1, we said, was to distribute. So that's not always necessarily the case. You don't always have to do distributive first, but in this case, it looks to be like probably the easiest way. Now we are distributing a negative 15/16 through, and so when we actually multiply negative 15/16 by 4/5, a negative 3/4 Q. And when we distribute negative 15/16 to 32/3, that turns out to be negative 10. Now you can do that by hand by just multiplying the numerators, multiplying the denominators and reducing, or you could use the, some canceling, or you could just use the calculator. But it turns out to be negative 10. And so that does quite a bit to simplify things. So now next step is to start undoing what's been done and bringing the constant terms to one side. Variables will be isolated on the other. So I'm going to go ahead and add a positive 10 to cancel out that negative 10. And that's going to leave me with a negative 6 over here and a negative 3/4 Q on the other side. So my final step is to undo the multiplying by negative 3/4 by either dividing by a negative 3/4, which is kind of tricky dividing by fractions. So as an alternative, I'm going to multiply by the reciprocal, which is a negative 4/3 on both sides. And that's going to leave me with to be 8, and that's the value of Q. So it looked a little messy, but it turned out to be quite a nice solution. So we're going to designate number 3, 5, and 6 to be you try questions. So we're going to pause the video now and try those 3 questions. Tune back in and check your answers. So the solutions to the 3 you try questions are: number 3 is negative 8, 5, 7/4 or 1.75, and number 6, W equals negative 12. So be sure to make a note if you had trouble with any of those 3, and make sure you ask me about them. I'd be happy to help. Let's turn the page. So far the equations we have solved have been kind of the typical equations that we're used to seeing. But we're next going to look at a couple of special cases that do occur. So solutions to linear equations can have single values, but they could also have a solution set to be all real numbers or to have no solutions at all. The solution to an equation is said to be all real numbers when you end up through the solving process getting something equal to itself. For example, if at the end you have an expression that says x equals x, or an equation that says negative 3 equals negative 3, or whatever, something being equal to itself. Usually what happens is the variables drop out and you've got some statement left that just involves numbers like negative 3 equals negative 3. If it's a true statement, then that means all real numbers will work in that equation, and this is called an identity. Now a solution of no solutions will turn out to solve to be something untrue. Like, for instance, if you end up getting something like negative 2 equals 5 or negative 4 equals 4 or something, and in most cases, if you've gotten to that last step, the variables have dropped out and you have 2 different numbers on either side, which prove to be an untrue statement. And when that happens, this is called a contradiction. And basically what that means is that one side is contradicting the other. So one side says negative 2, but the other side says 5. That's a contradiction. And that is a signal to you that there are no real numbers that satisfy that equation. So there are no solutions. So we're going to go ahead and take a look at a couple of special cases next. So number 7, let's following our normal steps. The first thing we would do is, of course, we would distribute. So we're going to distribute that 5 through to each part, and that ends up to give us 5 minus 5c plus 8c. And on the other side we have 1 plus 3c. Now next step is to simplify both sides by adding like terms. And so if we put our like terms together, of course we're going to put the c's together over here, and that gives us 5 plus 3c. And on the other side 1 plus 3c. So the next step would be to move the variables, and so usually I try to find the variable with the smallest coefficient and move from one side to the other. In this case, they're both the same. Subtracting 3c from both sides. And as it turns out, when we do that, because we have the same variable and coefficient on both sides, they both cancel out, leaving us with 1 equals 5. So we know that that is definitely not a true statement. That can never be true. So that's one of those contradictions. That's telling us that that means there must be no solutions to this equation. So we would say no solutions, or we'd use the M. So number 8, we're going to go ahead and do that distributive property. So we distribute the negative 8 through. Gives us a negative 8x, and negative 8 times negative 5 is plus 40. So 40 minus 8x equals negative 8x plus 40. Well, those sides look pretty similar. So we start to move. Say we didn't notice that, and we just started moving the variables. So we want to use the variable that has the smallest coefficient. Again, the coefficients are the same. That's usually kind of a signal. So when I add 8x to both sides to try to move the variables to one side, it ends up that in both cases the variables just cancel right out and leaves me with a statement that says 40 equals 40. Now we know that 40 is always equal to itself. That is true always, and so that turns out to be one of these identities. And what that tells us is that all numbers, all real numbers, must be solutions. So we either say that, or we'll use the all real or the real number symbol. That's that R with the double bars. So in our examples so far, we've been solving equations with single variables, and our goal was to try to solve and get a single solution. And we saw that doesn't always happen. There are some special cases. But sometimes you're working with what are called literal equations, and these are sometimes are their formulas or whatever. They're equations that involve more than one variable. And sometimes it might be more advantageous for the equation to be solved for a different one of the variables. So for instance, the formula distance equals rate times time. That might be something you've used in science before. Now that formula works great if you know the rate and the time and you're trying to find the distance. But let's say you want to find the rate. Well, finding the rate would be easier because you'd have to be given the distance and the time if you had your equation solved for rate or for the r. And we could do that by just getting r by itself, by just undoing the operations, going in this reverse or inverse order to rewrite the formula so it says rate equals distance divided by the time. So that's what we're going to be doing in this next section, is taking formulas, in most cases these are formulas, and solving them for a different variable that might meet our needs for different scenarios. And basically there's 3 steps we want to follow when we do that. The first thing is to locate the variable that you are asked to solve for in the equation, and maybe box it in. That's a good idea, to put a little box around it so that it really stands out. That's what eventually you want to have all by itself on one side of the equation. Step 2, to identify the operations on this variable that are being done and the order in which they are applied. And finally, step 3 is to use inverse operations to undo those operations and isolate that variable. Taking a look at our first example, you may recognize that formula C equals 2 pi r as the circumference formula for circles. So let's say we wanted to solve for pi. Maybe you've actually talked in class before about what pi is, and it's the ratio. It's the ratio of the circumference to the diameter in any circle, or in this case, the circumference to 2 times the radius, which is also the diameter. And solving for pi, we could see that. So this is it's not really a variable. In this case, pi is not a variable, it's a number, but this is what we want to solve for. That's kind of small, so that was the best I could do at boxing in what we want to solve for. But the 2 operations that are being done to pi are it's being multiplied by 2 and it's being multiplied by r. So all we have to do to undo those is just do the inverse of those, which is instead of multiplying, we would divide by those same 2 things. So dividing by 2r, and so when we have solved for pi, then it would be equal to circumference divided by 2r, or twice the radius. Now you may recognize this next formula from geometry. A capital A equals 1/2 little a times P is actually the formula for regular polygons. It means area is equal to half the apothem times the perimeter. And if we wanted to solve for the apothem, for this part right here, there are two things being done to little a. And the first is it's being multiplied by 1/2. So I could divide by 1/2, or I could multiply by 2. So I could do that, and then it's being multiplied by P, and so I could divide by P. So that's actually the first thing I'm going to do is I'm going to do this separately. I'm going to divide by P on both sides. So now I have capital A divided by P equals 1/2 times little a. And so then for my final step, instead of dividing by 1/2, which gets into dividing by fractions, I'm now going to instead multiply both sides by 2, because multiplying both sides by 2 then would cancel that 2 out and leave you with a final rewritten formula as little a equals 2 times capital A over P. Now that 2 can be out in front, or it can be on the numerator with the a. So again, just following these three basic steps, we're able to rewrite formulas for different variables or even for just different numbers. Look at one more example together, and we'll leave the next 3 for potential you-try problems. So notice in this equation, they would like us to solve for b. So again, I'm going to circle the variable I want to solve for, and I'm going to look at the 2 operations that are being done. Well, the first thing that's being done is it's got a being added to it, and then that entire thing is being divided by c. So the first thing I want to do is get rid of this c, and so to do that, I could simply, because it's being divided by c, I could multiply both sides by c, and then what that would do is cancel out that c on the bottom and leave me with just a plus b equals 5 times c. And then I want to get rid of the a so that b is all alone, so next I'm going to subtract a from both sides. And that leaves me with b being equal to 5c minus a, or negative a plus 5c. And let's go ahead and designate 12 through 14 as you-try questions. So let's go ahead and pause the video and try those, tune back in to see the final result. All right, so thanks for giving those a try. You can see how this would be a really important skill, especially like in number 12. That is basically what we do when we try to put something in slope y-intercept form, although this time we were solving for x. And in that situation, we would be solving for y. Or, maybe rewriting a formula like in number 14. That happens to be the formula for the sum of the angles in any convex polygon. And so maybe instead we want to, we know what the sum of the angles is, and we want to know how many sides there are. So this would be a way of rewriting it so it's more tailored to our needs. So our very last learning goal is to really look at proportions and proportional equations, and also being able to write proportions to solve problems related to rate problems, percent problems, and similarity. So you may recall the means extremes property or the cross products property or whatever that basically says if you have 2 fractions that are equal to each other, which is called a proportion, that the cross products of that proportion should be equal to each other. So in this case, if a over b equals c over d, then a times d, so with the cross products, a times d should equal b times c. So the cross products should be equivalent. And we use that idea when we solve proportions. So I know that's kind of hard to see those little arrows, but that's kind of the graphic, is showing that the cross products must be equal. So to solve equations that involve proportions, we use the cross products property. So in this case, number 15, we could multiply across the equality sign, multiplying the 5 by the x plus 4. Now, don't forget that x plus 4 is a quantity, so that would require us to distribute, and that would be 5x plus 20. And that should be equivalent to the other cross products, or 2 times 3, which is 6. And of course, that gives us a nice simple equation to solve. All we have to do is get the variable all by itself by subtracting 20 from both sides, leaving us 5x is equal to negative 14 and then dividing by 5, which if you gave a decimal value for that would be negative 2.8. And we'll designate number 16 a you try question. So go ahead and pause the video real quick. Try number 16 and tune back in to see how you did. And the correct answer for number 16 is negative 2/5 or negative 0.4 as a decimal. So using this idea of a proportion, we can solve percent problems. Now, there are two different ways that we're going to look at to solve percent problems, but the first one is going to be to utilize this idea of proportional, writing proportional equations. So a percent can be expressed as a ratio, and it's actually a ratio of how many out of 100. And so you can use the proportion below to solve percent problems. So we're going to take a look at this. Percent out of 100 equals part over the whole. Now, another way that we can do percent problems is to use this basic equation, which says the whole times the percent equals the part. Now, one way is not any more correct than the other, so you decide. We'll do some problems both ways, and you decide which works better for you. So let's go ahead and turn the page and take a look at some of those examples. So number 17 is about a poll that was taken a day before an election. Now, that's pretty timely. We have an election coming up. And it showed that 22.5% of voters plan to vote for a certain candidate. If 1,800 voters participated in the poll, how many indicated that they planned to vote for that candidate? So using method 1, which was the proportional way, we can take a look at the part over the whole equals the percent over 100. So taking a look at the important information, we were given the percent of 22.5% of voters plan to vote for a candidate, and if 1,800 voters participated, so this 1,800 represents the whole number of people that voted. This 22.5 is the percent, and we are looking for the part that planned to vote for this candidate. So we are looking for part. And if we set that up in this first method, we would say the percent, which is 22.5 out of 100, must equal the part, which is what we're looking for, so we'll call that the unknown, or x, over the whole of 1,800. Now we could simply do the cross products and solve to answer that question. 22.5 times 1,800 is 40,500. And that's supposed to equal 100 times x. So divide both sides by 100, and we find out that the number of people that were going to vote for this particular candidate was 405 people. Now, if we set this up the other way, the first thing we need to do is convert our percent to a decimal, and we do that by taking the percent and dividing by 100. And so that percent is 0.225, and the whole is what we're given, which is 1,800, and we're looking for the unknown, which is the part. So you can see that this is going to produce the exact same answer. 0.225 times 1,800 is 405 people. So either way that works for you. I prefer the proportional way, but that's because I work a lot teaching geometry with similarity and proportional figures. So I'm used to working with proportions a lot. And speaking of similar figures, recall that similar figures are the same shape, but not necessarily the same size. And they have congruent angles, but their sides are proportional. So you may remember when we studied similarity in geometry, we were able to use proportions to find missing links in similar figures. So taking a look at this example, the tree in front of Luca's house casts a 6-foot shadow at the same time as the house casts a 22-foot shadow. Actually it says foot, but typo. If the tree is 9 feet tall, how tall is the house? Well, our first goal is to try to get a picture that sort of, even if it's kind of a rough picture, that depicts the situation. So it says that Luca's house casts a 6-foot shadow. So, sketch a little picture of Luca's house. And the shadow, of course, is on the ground. So there's a picture of Luca's house in the ground. And at the same time, a house, oh, I'm sorry, this was the tree in front of Luca's house, but anyway, that's fine. But there's also a tree that casts a shadow as well. So we'll draw a picture of the tree, and of course we don't know how these relate to each other in terms of size, but we'll get the measurements in here in a second. So we've got a tree with a shadow and a house with a shadow. So the tree in front of Luca's house casts the 6-foot shadow. So this tree has a 6-foot shadow at the same time that the house casts a 22-foot shadow. So the 22-foot shadow. Now we know that the tree is 9 feet tall. So the tree itself is 9 feet tall. And we'd like to know how tall is the house. So the unknown, the thing we're looking for, is how tall Luca's house is. So there's lots of different true proportions we could write about this. If these are casting the shadow at the same time of day, then we would say that they are proportional. And so one way we could set up a proportion would be to compare the two heights of the actual things to their shadows. So we could say x, which is the height of the house, over 9, and again remember this is in feet that we're measuring, would have to equal 22 over 6. Now we could also say x over 22, so compare the height of the object to its shadow, and then must equal 9 over 6. But any of these proportions will always give you the same equation when you do the cross products, and that cross product would be 6x, right? And then 9 times 22 gives us 198, and finally dividing that by 6 gives us a value of 33, and so to answer the question, we would say that Luca's house is 33 feet tall. We got to make sure that when it's a real life problem, we want to represent that with correct units. So our final example is another real life problem. So one of the primary goals of mathematics is to describe real life problems and to solve problems involving quantities. I know that oftentimes students are scared of real world problems, and I think a lot of it is just not having a lot of exposure to it. So we'll try to do something about that in this course. But and anyway, this would require us to translate from words to algebraic equations. And when we do that, the first step is to establish a variable to describe the unknown. So figure out what you want to know and assign a variable to it. Step 2 is to describe the situation using that variable. Next we solve the equation, and finally we answer the real life word problem, so including units and any other explanation that might be needed. So here's an example for you football fans out there. In 2004, 3 wide receivers for the Indianapolis Colts caught a total of 37 touchdown passes. Now you may not know this, but Peyton Manning, that was his team. And he just won a Super Bowl this past year. So Reggie Wayne was one of the receivers, and he caught 2 more than Brandon Stokely. And Marvin Harrison caught 3 more than Reggie Wayne. How many touchdown passes did each receiver catch? Now that sounds pretty complicated because we've got 3 different people, and they together have a total of 37 touchdowns. So the first thing I would do is, even before I establish a variable, is I would kind of just write more of like a word equation to describe the situation. So I would say something like Reggie plus Brandon plus Marvin, or I'd use their last names to say they all together equal 37. Now I'm going to choose someone to be the variable, and I'm going to think about, as the wording goes, it says Reggie Wayne caught 2 more than Brandon Stokely. So I thought the first comparison was between Reggie Wayne, and he caught 2 more than Brandon Stokely. So I thought I would call Brandon Stokely X, and then that way I could describe Reggie as being X plus 2 because he caught 2 more than X. Now it says that Marvin Harrison caught 3 more than Reggie Wayne. So that actually could be described as whatever Reggie Wayne caught, which would be X plus 2, but then 3 more than that would be plus 3. So we have these 3 receivers that all together caught a total of 37 passes. Now as we put our like terms together, we have 3 X's, and add the constant terms together, we have a 2 and another 2 and a 3. That adds up to 7. Set that equal to 37 and solve from there. So we'd have to subtract 7 and divide by 3. So subtracting 7 would give us 30. equals 3x dividing by 3. That means x is 10. And now to answer the question about how many each person caught, we would know that Brandon, he caught 10 touchdowns. We know that Reggie Wayne, he caught 2 more than that, so he must have caught 12 touchdowns. And finally, Marvin Harrison caught 3 even more than Reggie, and so he caught a total of 15 touchdowns. And of course, they all add up to that, I think that was a record of 37 touchdowns. And that's going to do it for our lesson today, so I'll see you in class.